Problem number three is that we have a simple Weber power plant. So it's we say simple Weber power plant. We have the boiler here, and then we have sort of a pump, and then we have the condenser, and then we have here the turbine that is sort of giving me out the work or the power. So this is boiler, this is condenser, and this is turbine, and this is pump. And it also gives me the state before and after each of those devices. So I can just write down, if I consider this as 1, so state 1, I have P1 is 100 bar and T1 is 520 centigrade. And at 2, after the turbine, of course the pressure will be reduced. So P2 is 0.08 bar and X2 equal to 90, which is the quality is 90%. And after the condenser, which is 3 in this case, you know the pressure doesn't change through the condenser, so P3 is equal to 0.08 bar, and what I know here is that I know that it's saturated liquid. So the state is also fully defined. And after the pump of course increase the pressure, so we go back to the high pressure, which is P4. This is 4. P4 is like P1, so it's 100 bar, and then T4 is 43 centigrade. So this is the information that we have about all the devices. It's good to see that we have actually two pressures here. We have the high pressures, which if you sort of cut it in two like this, you will have the high pressure after the pump, which is in the boiler, and the low pressure in the condenser. Um, Otherwise, you have also I think most of the states here are known. And then it tells you that the mass flow rate is given. As you can see here, the mass flow rate is given as, so I can write mass flow rate here through the cycle is 109 kilogram per second. And you can and also if you heat transfer, kinetic and potential energy can be ignored. Determine the mass flow rate of the cooling water, which is in the condenser here. You have the cooling water coming in like the previous problem, coming in with the temperature it's 20 and leaving at a temperature of 35. It's actually similar to the previous problem. Uh, and then it wants us to find the thermal efficiency. And finding thermal efficiency, it means that we need to sort of find for all the devices, we need to find the work and we need to find Q. So we need to apply first law of thermodynamics for all the devices before we can find the thermal efficiency here. So let's start with the assumptions. Now the assumptions is it's good to so the assumptions here is that um, the major components are working, all the components are work at steady state, which means the mass flow rate coming in is equal to the mass flow rate coming out. For the turbine and the pump, we are considering that the control volume is equal to 0. Um, so the heat is not leaving, there's no heat leaving the pump or the turbine as a control volume. And then we have also kinetic energy, potential energy are also can be ignored. And for cooling water, we already said that for cooling water, if it's a compressed liquid, we always take the enthalpy at HF at the temperature that we have. This is how we do it. We go to the table, temperature tables, and we read HF, and that's going to give me the H for the cooling water, as we're going to see. Okay, then we start with state 1. So now, because the challenge here in such problem, the challenge is always to find the enthalpies, because the other thing is not difficult. We know now the first law of thermodynamics for an open system like a boiler, how it looks like, or turbine or condenser, and we know that it's always the mass flow rate multiplied by the change in enthalpies. So testing the enthalpies, if you know all the enthalpies at 1, 2, 3, 4, then I think you can calculate most of the things that they are asking about. So we start with 1, which is so let's start with state 1. As you can see, state 1, I have the pressure. I'm just showing you at the table for the table here. It's good to because I will show you a list at the end. But it's good to so how we can find the enthalpies, and you can look for P1 for state 1, and now we're in the turbine. I can just do it here. This is my control volume now for the turbine, and this is 1, at least this is 2. And at 1 we said I can bring it back immediately, or you can look to it here. It was pressure the pressure here was P1 was 100 bar, and temperature was 520. It's T1 is 520 centigrade. And if you go to the superheated tables, of course you can again check if you're in the superheated or not, but here I know that I'm in the superheated region, and I have, this is the pressure, which is 100 bar, and the temperature is 520, and then I can read H1. So this is H1 I can write here is 34251. So I know H1 now. Now H2, what is H2? Remember, at 2 we have P2 is 0.8 bar, and we have X2 90. So what we know here is that we know that P2 is 0.08 bar, and then we know also that T or X2 is 93 or 90, given as 90. And by knowing this, I can go to the saturated tables now at the pressure base, and this is the pressure that I have, right? And I have also X2, so what I do is that I can H2 is equal to HF plus X HFG at P equals 0.08 bar. So this is where I go, and then I read this is F and this is HFG. X I have, and that's going to give you H2, and I can write it down if I have it somewhere here. I think I have it somewhere, and I can write that H2 is 2336.7. Right? Now H3 is the condenser now. So now we are done with the turbine as a control volume. Now we take the condenser as a control volume. So what do we have? We have this is a condenser. Very important here because he asked me to find the cooling water. But let's focus now on H3, which is because this comes from the turbine here, and the steam goes, what do we know about? I know here that the pressure is 0.08. I know that it got in here as sort of steam mixture, vapor, liquid, but it tells me that at 3 here the pressure is 0.08, but it also tells me that it went out as a saturated water. It's exactly as if it tells me that it's at the same pressure here, 0, but this time H3 is actually HF because it goes out as a liquid. So I can see H3 in this case is 173.88 kilojoule per kilogram. So now I have H1, H2, H3. Let's see what's H4. Now H4 is after the, I need to come back here just to not lose the track. H4 is telling me that the pressure is now, after the pump, the pressure is 100 bar and the temperature is 43 centigrade. So what I need to do here is that this is a temperature that I have, and I know it's after the pump. I know it's water still liquid, and it's at 45 degrees. So I go to the same table, and then I can read H4. So H4 is actually HF at T equals 45 centigrade, and that's going to give you 188.45 kilojoule per kilogram. So what I do have now is that I have all the enthalpies that I need, and I can have I just made a table here because I also need the enthalpies of the cooling water. And the enthalpies of the cooling water, remember we said that the cooling water are coming in at 20 and it's going out at 35 centigrade. So for the cooling water, let's say the inlet of the cooling water. So this is the cooling water. We said if you have a cooling water or compressed liquid and you want to find the properties, you go to the saturated tables at the temperature and then you read HF. So as you can see, the inlet is 20 and this is H at the inlet, and that 83.96 point, 83.96 kilojoule per kilogram, and this is when the water is setting, when it takes the heat, of course, increase its temperature to 35. So this is the H after the or at the outlet of the cooling water. So now I have all the enthalpies. So things I can make now a table like this, and I can write. You already have this table, and that table will look like this. I will do and here I will write the state. So this is the state number, this is P bar at this state, this is T, the things that I know, this is X if I need it, and then this is the enthalpy, kilojoule per kilogram. It's good to do it in the table because that's going to help you in sort of having it clear before you start the calculation. So at state 1, we already said that the pressure is 100 bar, 520. X is actually undefined, you can see larger than 1, and we just read it from steam table, which is, I can write it A6, and that was 3425.1. And then state 2, we have 0.08 bar, and then it's a T saturated, and X is 0.9, and that read 336.7, and that's from A5. And then from 3 you have again 0.08 and bar, and that is T saturated. Doesn't have any meaning actually. It's here because it's compressed liquid. That is 173.9. That is A5, table A5. And 4, it's 100 bar again. It's 43 centigrade. That is also, X has no meaning because it's a compressed liquid, and you read it from the saturated table as 188.45. And the water inlet now, because this is for the steam, and now at cooling water inlet, so cooling water inlet and cooling water outlet. It's 1 atmospheric, and this is the same as 1 atmospheric. This is 20 at the inlet, and it leaves at 35. It has no meaning, X, and that's you read from the table as 8396, of course, kilojoule per kilogram, and that is 146.68 kilojoule per kilogram. This is A4. This is also from A4, and also this is from A4 table, which is saturated mixture temperature base tables. Now, if you have this, now you can go to solving. I can take it here and see. Now, the mass flow rate, we know this. Now we have done it in the formal, the previous problem also, that the mass flow rate for the cooling water now is actually the mass flow rate of the steam, I will say here, or the, let's say, working fluid multiplied by the difference in enthalpy for the working fluid divided by the different for cooling water out minus enthalpy for cooling water in. And if you do so, you remember this is given, those are already, we have already read them. So if you put all the numbers here, you will get that the mass flow rate for the cooling water is actually 3758.7, and that is kilogram per second. That's A. And B, it's asking me to find the thermal efficiency. And for the thermal efficiency, we know the thermal efficiency is work net divided by Q in. And work net is actually work of the turbine minus work of the pump divided by Q in. And work of the turbine now, work of the turbine is the mass flow rate multiplied by H1, H2. We know this by now. This is the first law of thermodynamics for the turbine. When everything else is zero. And if you do so, you will find that this is 180,636 kilojoule per second. And for the pump, it's the same. The mass flow rate is constant, and H4 minus H3, which is the difference in enthalpies after and before. And if you do so, you're going to get this is 1685 kilojoule per second. And Q in is the mass flow rate multiplied by H1 minus H4. This is for the boiler, and that's going to give you 352,746 kilojoule per second. And to find the efficiency, if you take those numbers and put them here, you will get the efficiency as probably I don't even have it here. I didn't do it, but I think you will find it as I can write it here just for records if you want to do this. So the efficiency is 33.2%.